Okay, so welcome to this next video in the theory of probability. In the previous video, what we did is we discussed the gamma distribution. In this video, what we're going to do is calculate the moment generating function of a random variable which is gamma distributed, and then what we're going to do is use the moment generating function to calculate the first and second moments, and then from the first and second moments we can calculate the variance of the gamma distribution. And obviously the first moment is the expected value, so we'll get the mean and the variance of the gamma distribution. Okay, so the basic setup is this. We have, let me just bring this down, alright, so keep it like there. Alright, so I can start here. So let's say here we have some abstract probability space here, and then we have some random variable x here, which is going to map you onto the positive real numbers. So every outcome in here is going to be ascribed a positive real number, so 0 but not including 0 up to plus infinity, and we're going to say that this random variable, this probability space here is going to be distributed gamma a lambda, which means that the probability density function of this random variable, the probability density function of the random variable big X as a function of little x, where little x is just some real number, is going to be equal to, well, it's going to be 0 on the non-positive real numbers. So it's going to be 0 if x is not an element, so not an element of the positive numbers, i.e. it's a non-positive number, and it's going to be equal to the PDF of the gamma function, which is 1 over the PDF of the gamma distribution, which is 1 over gamma of the 1 over the gamma function evaluated at this parameter a times lambda x to the power of a times e to the negative lambda of x divided by x. So that is the PDF of the gamma distribution on the interval x as an element of 0 to infinity, so on the positive real numbers. Okay, and we now want to calculate the moment generating function for this. So remember, the moment generating function is another way of representing the probability distribution on this probability space of real numbers, of positive real numbers in this case. The probability density function stores within it all the information of the probability distribution on this probability space. Remember, the probability distribution is just another name for the probability measure on a probability space where the elements of the probability space, the outcomes in the probability space, are just real numbers. So that's what the probability distribution is, and there are many ways of representing it. So if you've got a discrete random variable, we've seen that the probability mass function is a good way of representing it. In the case of a continuous random variable, which this one certainly is, the probability density function is a good way of representing it. Similarly, you have the cumulative density function, which is a good representation for both discrete and continuous random variables, and another one is the moment generating function, which again works for both discrete and continuous random variables, and it's a theorem that I have never in this playlist proven to you, but the moment generating function does uniquely specify a probability distribution, and if you are given a a moment generating function, there is only one probability density function that corresponds to that. So basically what we're going to do is find the moment generating function that corresponds to this probability density function. And the way that one does that is the moment generating function of this random variable x as a function of little t is defined to be equal to the expected value of e to the tx. So effectively what you do is you take a transformation of this random variable. You take the transformation which is e to the t of x. So these are all positive real numbers here. So if we think about this function here, this function, let's imagine for a moment that t is a positive number. The exponential function looks like this if it's a positive number. If t is a negative number, obviously it looks more like that. Again, we are only interested in what it is on the positive. Oh dear, sorry that you can't see this. Let me pull that down. Ignore what that is. That's from the previous video. But our set on which this function is acting is just the positive real numbers, those there. So basically what this function is going to do, it's going to map the positive real numbers onto a subset of the positive real numbers. If t is positive, then that subset of the real numbers which it's going to be mapped onto is going to be the numbers from 1 upwards. In fact, no, it's not going to include 1. Why? Because what number would correspond to 1? Well, it would be the number 0. If you plug 0 into the exponential function, whatever t is, the value which gives you 1 is going to be 0, and 0 isn't included in your domain here. So you're not going to get the point 1, but all of the points upwards from 1 onwards, so from 1 to plus infinity, you're going to get if t is greater than 0. So let me just make sure this is in the camera. Yep. If t is greater than 0, that's what you're going to get. If t is equal to 0, obviously you're just going to get 1, 1, 1. So you're going to get that function there. That's not a particularly interesting one. But if t is less than 0, obviously what you're going to have is a curve that looks more like this one here, a negative exponential. So the positive real numbers in that case are going to be mapped onto the interval from 0 to 1, basically, and it's going to go down from 1, and it's going to converge on 0 as you get bigger and bigger and bigger. Okay, so you're going to be mapped onto a subset of the real numbers. So one of these subsets you're going to be mapped onto, and basically what you then want to do is view the composition of these two random variables as a new random variable and take the expected value of this random variable here, okay? So the way in which we can do that is we can just apply Lotus, basically. We can say, okay, every value in here has a corresponding value back here. So if we want to calculate the expected value in here, what we need to do is take its value in here and multiply it by the probability that you are that value, basically. And the probability that you are that value is just the probability density from here, basically. So by Lotus, what we can say is that this is going to be equal to the integral from, we can do it from 0 to infinity because the domain is on 0 to infinity. And then we put in the value of the point in here. So if you've got some point in here, let's say little x, it is mapped onto e to the tx, basically. So that is going to be your value overall. So we put in e to the tx, and then what's the probability of that little value x? Well, it's going to be the probability density function of that value x. So I'll plug that in. 1 over gamma of a, lambda x to the power of a, e to the negative lambda of x over x, and then times dx, because that's a probability density function. If we multiply it by a tiny little interval dx, then that's going to turn it into a probability, is what you can imagine. That's a good intuition for what that's doing, basically. And then what we do is sum over every single possible value of x between 0 and infinity. That's the intuition of what that is doing. Okay, so let's compute this integral. So this is the integral from 0 to infinity of, well, 1 over gamma of a is just a constant, so I could have pulled that out, couldn't I? I haven't really got space, but I'll put it up here. 1 over gamma of a, so we'll pull that out. Then we get lambda x to the power of a, e to the negative lambda of x, and we'll combine that with the e to the t of x, so we'll get e to the negative, what should we have? We'll have negative lambda minus t to the power of x, and I do apologise, I'll pull this out here. Right, okay, and then we've still got our 1 over x. Is that everything? So that's done, this is done, this is done. The 1 over gamma of a is right at the front, so let me just complete it by putting the dx there. Okay, now this looks very much so like a gamma function here. So what we're going to do is basically make a substitution and hope that what we'll get is something that we can write in terms of gamma functions. Okay, so I'll call it there, and we'll continue this in the next video.